polynomial base, so it's not going to be that bad. It has to be the vector space of functions spanned by the linearly independent functions. Those. Find the antiderivative of this function. Now you know how to do it by hand, it's obvious. But how do we do it using matrices? Alright, so we have 1, we got x, we got x squared, we got x to the third. Now we're taking antiderivatives. Depending on what you're working with, you can keep going. X to the fourth, x to the fifth, x to the sixth, all the way up to x to the n. So you can define your antiderivative space based on whatever you're working with. So from your infinite set, you select the ones that are relevant. So if I come up with a nice span of possibilities, then I can use it to apply to many different situations. So then, using my reverse power rule, I know that I have an x, 1/2 x squared, 1/3 x cubed, 1/4 x to the fourth. Way more than we need, but just for instructional purposes. All right. So the space that I need starts with a function to the first power and ends with a function to the second power. Right? So that's what I'm up against. So I need these guys. So this one could be written as zero start with the one that you want. Is it really only a 2x2? I don't remember it being a 2x2. Oh, we're going to find out in a second. All right, so our antiderivative matrix, if we're working in the space that spans from power of 2 to power of 3, we're looking at 1/2. This monomial could be thought of as 1/2 x to the second plus 0x to the third. And this one would be 0x to the second plus 1/3 x to the third. So that's where our antiderivative matrix comes from. And it's, again, only dealing with the relevant components. The function that we're given has coefficients still in the same category, the same region, subset. That's the word. So we want to map from power of 1, power of 2 to power of 2 to power of 3. So coefficients here, 3, -2, matrix multiply. We're looking at 3/2, -2/3. Because in our antiderivative space, we're looking at powers of 2 and 3. This would then become 3/2 x to the second minus 2/3 x to the third, plus a c because calculus. So this is what you want to map into. Right? The one previous to this was a little bit different because the space prior to your derivative and post-derivative was the same. It had the same dimensions, it had the same characteristics. Here, you're mapping into a space such that the powers are increased by 1. Right? So your initial function vector should have whatever powers are relevant to that function vector. Corresponding to that, you have your matrix that is related to your antiderivative vectors. Right? So what does this become? What does that translate into in the vector in this particular space? Only in the subset of the entire polynomial space. All right. So once you define this, multiply, you have your antiderivative. All right. Obviously, I mean, it's more complicated if the antiderivatives of your parent functions are more complicated, but if they're relatively straightforward, it's not that bad. So, for example, just to do one more, and I'll take this as a typo. If I needed something like the antiderivative, let's say, of 3x to the third minus, I'll say x to the fifth dx, just so I don't have too much overlap, or any overlap. That would, we'd be looking at this space here, this subset. All right, so my antiderivative space is going to span from power 4 to power 6. All right, so if I were to represent this in terms of only powers of 4, 5, and 6, I'd have coefficient of 1/4, 0, 0, because I don't have a power of 5 or power of 6 associated with this guy. This would be 0, 1/5, 0, and this would be 0, 0, 1/6. My initial state vector, use a slightly unrelated term, but it feels right, would be related to your integrand. So this spans from power of 3 to power of 6, but that's what we want to transform. We want to transform from integrand space to antiderivative space. So 3 for the power of 3, 0 for the power of 4, and -1 for the power of 5. Very easy to multiply because with polynomials for antiderivatives anyway, it's, well, I can't think of any. Well, first off, I'm not going to give you any situations that vary from this type of scenario on the test, but when it comes to just simple polynomials, they always end up being diagonal matrices, so the work is very easy. 3/4, 0, -1/6. And again, we're living in antiderivative space. So 3/4 x to the 4th minus, well, I kept it maybe a little too simple, but, and then pop a plus c because it's an indefinite integral. You can do a quick check, Ruski. 6, thank you. So yeah, but it's going to be 3x to the third, and once I make this slight correction, this would differentiate down, oops, that's too big, to -x to the 5th. All right. The one, I mean, I think you could probably conceive of the pretty significant flaw of this approach is, unlike the derivative approach where you can continuously multiply your resulting vector, you know, kind of like in that Markov chain kind of process, this way kind of falls apart because you do have to account for your constant, right? So you'd have to establish a different antiderivative vector or a matrix for the next iteration to account for the constant, almost to the point where it doesn't really make it overly worth it. But it's one of those cases where if you had, you know, if you had this available and there's like 10 questions, like, oh yeah, this is pretty quick. I can do it very easily, right? But also you could do the reverse power rule very easy as well. So kind of hit her.